And hello, everybody, and welcome to the first of 4 webinars as part of the spring lineup of PDH-bearing webinars being given by Atlantic Testing Laboratories this spring. So my name is Chris Kelson. I'm a senior geologist here at ATL. My job here involves anything and everything related to geology, petrography, and especially forensic analysis of concrete, including petrographic analysis of concrete and air void analysis of hardened concrete. I'm tag teaming with Mr. Steve Moore on this particular webinar. I'll be giving the first half of it, and then Steve will do the second half. But we're talking about the same topic overall. We're discussing the corrosion of embedded steel reinforcement in the concrete. And again, just a reminder that this is the first of 4 webinars in the spring webinar series from ATL. If you're interested in the other webinars after this one, please refer back to the email that was sent out that you saw this advertised in and register for it. The same email will get you the links to the other ones as well. Now, in lieu of being able to stand in front of everybody in person and use a laser pointer on the screen, the best I can do is use my mouse cursor, which you can see moving on the screen. So as I point things out, please keep an eye on the mouse cursor. Okay, so we're going to, I'm going to go back to that title slide. We're going to talk about each of these individual pieces in turn. So we're going to talk about concrete. We're going to talk about reinforcement in concrete, and then we'll talk about the corrosion of embedded steel and concrete. So we're going to, and steel itself. So we're going to walk through each of those topics piecemeal. Just a quick official definition of what concrete is. We all know what it is. Here's the official definition, right? Composite material consists of a binding medium, embedded particles or fragments of aggregate inside of it, and the hydraulic cement. Concrete acts as a binder for everything. Just to give you an idea of how important concrete is in the grand scheme of things, worldwide, it's the second most consumed material only after water. In 2020, so this is about 5 years old, these stats, China was definitely the world's leading producer and consumer of both cement and concrete, followed by a distant second India, followed by Vietnam, then US, and the rest of the world. It seems like the number 3 and number 4 spots here, Vietnam and US, toggle back and forth depending on the source that you look at, but you're getting the impression, just to get an idea of just how much concrete is produced by China. In the span of 3 years, they produce the same amount that the US has produced in all of the 20th century. So they're outstripping everybody on the planet. Every year, about 5 billion cubic yards of concrete is used worldwide. That's the equivalent to over 913 Panama canals worth of concrete. And at least back in 2019, about 8% of the global CO2 emissions were a result of concrete production. So the stats are a couple of years old, but you're getting the impression about what a big player concrete is in the worldwide, and also what sort of impacts it has from a natural resource and environmental standpoint. Let's spend a couple minutes and discuss steel, because steel is used as we embed steel into concrete. So what exactly is steel? It's a man-made alloy. It's not natural, right? So it's a man-made material composed mostly of iron, but there are other metals that are added to it in various proportions and for different reasons. So again, the major ingredient in steel is iron, and iron The element is the fourth most abundant element in continental crust, only after oxygen, silicon, and aluminum. Notice I said continental crust. Oceanic crust will have more aluminum, more iron, but we're just referring to continental crust. So the major iron ores from which iron is recovered include hematite and magnetite, and those are both iron oxide minerals. The formulas for each are shown there. Now, in order for us to make steel, we have to recover the iron from those minerals, and we do that via a process called smelting. And smelting, in 10 words or less, is simply the process that lets us remove unwanted elements from an ore-bearing rock so we can keep the elements that we do want. In the case of iron, we're removing the oxygen, say, from either the hematite or the magnetite by the addition of another element such as carbon, okay? So it depends on which metal we're trying to extract out of the ore, but in this case, with iron, that's what we have. The only way that's not necessary is if we're dealing with metallic elements that occur in their native state, meaning that they're not bound up to any other element. So an example of that would be native gold or silver or copper, right? Platinum, those elements can occur in their native form just by themselves. But iron is not like that. It's most commonly associated with oxygen, although there are other possibilities that we'll discuss momentarily. I briefly mentioned that there are other elements that you can add to the iron to make steel, different types of steel, and depending on the element you're adding and how much, it gives you a kind of a different flavor of steel. So here's just a really brief delineation of the different types of steel. For example, cast iron or plain steel, high strength steel, stainless steel, and the different elements that you see are added to each of the to the iron to give different in different proportions to give different physical and chemical properties to the steel. Stainless steel, for example, the big ingredient is chromium, the element chromium. That's what makes stainless steel stainless steel. At the bottom of the list, you can also see there are another dozen or so elements that can also be added to steel. So steel is more complex than one typically realizes, and you can see why. Just from an interesting historical note, the first production of steel, quote unquote, in a loose sense of the word, was about 1800 BC when some ironware was discovered, had been made. So now the question is, why do we embed steel or anything else into concrete? What's the purpose of embedding objects into concrete? As you probably already know, concrete possesses really high compressive strength, but a relatively low tensile strength. So to combat that, reinforcement is embedded into the concrete, which helps accommodate that tensile stress and therefore strengthens the concrete. That reinforcement can be anything. It could be steel bars that we call rebar, could be FRP bars, fiber reinforced polymer bars, steel mesh or steel or synthetic fibers, etc. So rebar isn't the only game in town, but it's obviously very commonly used and commonly seen. Another historical note at the bottom of this slide: in the mid 1400s, rebar was first used in masonry. In the 1800s, it was used in concrete. So steel reinforced concrete is a big deal, as we all know. I've listed a relatively short list of really important infrastructure aspects of infrastructure that contain steel reinforced concrete, and it's a short list, but it includes probably most everything out there. Very important. Reinforced concrete is very important to our society, obviously. But steel isn't perfect. There are a couple problems. Well, one big kind of problem, quote unquote, that we run into when using steel, and it stems from the fact that steel is not a naturally occurring material, right? It's man-made, so it's thermodynamically unstable in Earth's atmosphere. And unless that steel is protected, the refined iron in it will try to revert back to its most stable form, which is its iron oxide form. So if you remember the chief iron ores, hematite and magnetite, those are all iron oxides. Those are stable on Earth's surface, right, in Earth's atmosphere. Well, steel wants to get back to that most stable form, iron oxide, unless it's protected, and it'll do so. Now the processes that affect the steel as it goes from affect the iron as it goes from iron and steel back to iron in its most stable form, or what we call oxidation and corrosion. And those two terms are different from one another, but they're often interchangeably used. So I think it's valuable to tease them apart and explain why one is different from the other and what they each mean. So oxidation is a chemical reaction that basically involves a metal losing electrons. Well, any element losing electrons, but in this case, iron, right? So if we have, for example, iron in it with a +2 valence state, that's ferrous iron. If ferrous iron is oxidized, it's losing an electron and therefore becomes a little more positive with a little more positive valence state. So it goes from a +2 to a +3 state, which is what we call ferrous iron. So that's an example of oxidation. It's just an element losing electrons. Corrosion, on the other hand, refers to a complex sequence of reactions, electrochemical in nature, between the element and its environment that involve oxygen and water. So now we go back to the idea that steel is unstable in Earth's atmosphere, which is in direct contact with the Earth's surface, and it's loaded with oxygen and water, and that's why steel will try to revert back to its native state, more stable state. Visually, this is easy to see, and we all know what it looks like when you have steel that's not protected by paint or some other coating, right? We know what this looks like. We know what happens. We have rust that forms, but the word rust is interesting because it's used as an adjective, it's a verb, it's a noun, right? I mean, like, is it rusting? Is it rusted? Is that rust? Did rust form? Like, it depends on how you want to work the verbiage, right? But we all understand what we're referring to. When we say rust, our brains typically think of the steel being kind of rotted away, for lack of a better term, but rust also refers to that orange and brown stuff that we see forming in the pits and craters of the steel. So it's just kind of this all-inclusive term. But we know what it looks like, and now we're understanding what's making it happen. But just for completeness sake, I'll let you know that there are minerals, there are naturally occurring compounds such as minerals that are also susceptible to oxidation and corrosion. An example of that would be the mineral pyrite, as you can see in the picture on the left side. Pyrite, otherwise known as fool's gold, right, has brassy yellow color, metallic luster, right? Cubic crystals. You can see what it looks like in its natural form. But the iron in in the pyrite. So pyrite is a combination of iron and sulfur, FeS2, but the iron in the pyrite and the sulfur itself want to revert to something that's more thermodynamically stable than FeS2. So over time, even the pyrite will start to, and the sulfur, I mean, the pyrite itself, but the iron and the sulfur will oxidize and corrode, and you will ultimately get something that an equivalent that you see on the right-hand side, where instead of a cube of brassy yellow colored metallic luster shiny pyrite, it's now rusty, right? For lack of a better term. It's because it's oxidized and it's corroded and it's changing. Now, if we happen to use aggregates, if we crush up rock that contain pyrite or other sulfide minerals related to pyrite, if we crush that rock up and we use it as aggregate in concrete, for example, we need to be careful about doing that, because the oxidation and corrosion that the pyrite will start to experience creates secondary products. In this case, it's that iron oxide, brownish reddish material you see on the right hand side, and the formation of that iron oxide material is accompanied by a volume change, right? So when you form that iron oxide material, the volume of the material is changing. And if that pyritiferous material, for example, is encapsulated in concrete and it starts to oxidize and corrode, well, it's going to expand and cause the concrete to crack as a result. So that's why petrographic analysis of material used as fill, or of bedrock being proposed to be underneath buildings, or for aggregate inside concrete, needs to be thoroughly petrographically examined to make sure that this isn't potentially going to happen. So now the question is, if we know that steel corrodes, why doesn't it corrode if it's embedded in concrete? Well, in a perfect world, the embedded steel in concrete won't corrode, because metals only corrode in acidic and not alkaline environments. And lucky for us, the pH of concrete, cement, and water in equilibrium with that is really basic. It's like a pH of 12 or 13. So as long as the embedded steel is within that highly alkaline environment, we're not going to experience any oxidation or corrosion of the steel. What happens is there's a what's called a passivity layer, which forms around the embedded steel when it's embedded into the concrete. Now, this passivity layer is really, really super thin, maybe a tenth of a micron. And remember, a micron is a millionth of a meter, right? So it's just tiny, tiny thin. But this little thin oxide layer essentially acts as a controlled, it's a control for very minimal oxidation or corrosion of the surface, and basically protects the embedded steel from oxidation and corrosion, right? I mean, it's not bulletproof. It slows it down to about 1/1000th of what it would be if it wasn't there, but it protects it, and that's important. So as long as that passivity layer, which is shown in the diagram you see here with that green layer, as long as that passivity layer is present, then we're okay. The problem is when the passivity layer is damaged or removed, or you're able to poke holes in it, then you're exposing the concrete to potential corrosion and oxidation and corrosion. So what breaks down the passivity layer around embedded steel? The list has 6 or 7 different things to it, but we're going to start off discussing the number one primary cause of the breakdown of the passivity layer, and that's chloride attack. So when I say chloride, I'm referring to the element chlorine. That's element Cl, right? Chlorine. But if it has a a negative charge associated with it, like a Cl-1 is shown here, we now call it a chloride, right? So chloride attack is the primary cause of corrosion of embedded steel. So where does the chloride come from? Well, if we're talking about concrete that's used externally, right outside, de-icing salts, or by definition, have a lot of chloride in it. Seawater has a lot of chloride in it, and also seawater, if it's sprayed on the building, not submerging the concrete necessarily, if you're spraying seawater onto concrete, that will introduce the chloride into the concrete. Understand, obviously, that concrete is porous and permeable, so water soaks into it, and moves within it fairly easily. So if there's chloride in the water, which is highly soluble, then it'll get down deep enough to where the embedded steel could be. Also understand that chloride could also be sourced internally within the concrete itself. So the cement may have chloride in it. Additives added to the concrete when it's being mixed may also introduce chloride. The aggregates themselves may contain chloride, and even mixed water might contain chloride. So chloride's everywhere, and it could be sourced both internally to the concrete or externally to it. The problem is we know that chlorides play a big role. Chloride plays a big role in the breakdown of the passivity layer of embedded steel and initiates corrosion and oxidation of the embedded steel. We know that's the case. The more chloride there is, the higher the risk of corrosion. We also understand that chloride is, like I mentioned before, highly soluble, so it's easily introduced into the concrete. But the problem is that we can't directly observe what it is I'm talking about, because the embedded steel is embedded in concrete. So it's hard to directly observe the interaction between the cement paste and the concrete and the embedded steel, because it's all encased in concrete, right? So a lot of this is kind of theoretical discussion, but we're pretty certain of these relationships we're discussing. Also note that the presence of oxygen and water have a lot to do with how much chloride you can have in the concrete or in the cement before it starts being a problem. And the PCA a number of years ago put out this in ACI 318, right? By weight of cement, they've listed the maximum amount of chloride that's acceptable for certain types of concrete. Now, notice that look at numbers 2 and 3 listed on here. So we have reinforced concrete exposed to chloride. The maximum chloride content by weight of cement is 0.15, but if the reinforced concrete is dry or protected from moisture, you can have up to 1 instead of 0.15. So again, the role of oxygen and water are really crucial here. But at the end of the day, chloride is not good to have in the concrete if it's got steel reinforcement. So we just talked about number 1 on this list. There are other reasons why that passivity layer can be damaged. I'll mention this for number 2. If the cement paste around the embedded steel is carbonated, that will also remove the passivity layer. So remember, the passivity layer is there when the pH is 12 or 13. If you carbonate the paste, then you're lowering the pH of that cement from 12 or 13 down to like 8 or 9. And that's enough to remove the passivity layer. So in a couple words, you carbonate cement by introducing carbonic acid into the paste. Carbonic acid is naturally formed from water and carbon dioxide. It's dissolved in water. That water with the carbonic acid gets into the paste. It interacts with the portlandite within the paste, and changes it to the mineral calcite, hence the term carbonation. So in the process of doing that, it's lowering the pH of the paste. Just to illustrate this, I'm going to give you a real world example from a project we worked on. So what we're looking at here is a vertical wall. This was the inside of a swimming pool, and the tile was removed off the inside of the swimming pool. But you can see that the cementitious grout underneath there, cementitious material underneath the tile, used to have some steel mesh, and you can see the strands of steel mesh as those brownish red lines across the face of this. We took a core into the wall of the pool, and there's a close-up of it. You can see that each of these reddish lines, reddish colored lines, used to be a strand of steel. Okay, look, it's not that anymore. It's clearly oxidized and kind of corroded away. When I looked at this under the microscope, when I was doing my petrographic work on this is what we see. So now we're looking at that in cross section. The pink color at the top represents the surface of the sample. This black colored blob at the top is a cross section of one of those embedded steel strands, and you can see that it's ratted out. It's got holes in it, and it's clearly not a solid piece of steel anymore. It's got roughed up quite a bit. When I look at this under polarized light, I can see that the surface down to that yellow line of this concrete has been carbonated. So why did that embedded steel mesh oxidize, which was causing the tiles to pop off, right? And that was the problem. The formation of iron oxide did that because the steel strand was, well, two things were happening, I think. Clearly the paste around it was carbonated, so the passivity layer was removed, and therefore oxidation and corrosion could just go to town. And also you're in a swimming pool with chlorine in it, right? So the chloride is probably getting in there too. This example is a good example of why a lot of these projects can benefit from both petrographic analysis and also be augmented by like water soluble chloride analysis too, at different intervals at depth, to really get a handle on how deep the concrete may have been affected by the chlorides. And then just to round out that list of what causes the passivity layer to fail, could be a function of temperature, could be a function of the surface finish of the embedded steel. Microbes could play a part in this. If the steel has been irradiated, if the embedded steel has been cracked due to stress, and also just time, which means if the more denser the material, the slower the corrosion might be too. So a lot of factors go into this, but at the end of the day, it's not good for embedded steel and concrete to oxidize and corrode. So I'm going to spend about 30 seconds here really topically discussing just a little bit of the chemistry behind why this happens. The picture at the bottom of the screen is showing a brown, it's colored brown, but that's our embedded steel, and there's concrete all around it. The green line represents the passivity layer, and whenever there's a hole in the passivity layer, the embedded steel is then naked and very susceptible to the onset of corrosion and oxidation. What happens in those holes of where the passivity layer is removed, we have an anode reaction, an anodic reaction, where the iron is being oxidized. Okay, the loss of electrons, and those electrons are released into the concrete. Those electrons then bind with oxygen and water to produce hydroxyl molecules, which are good because if this is happening on a very small scale, then the formation of the OH groups will kind of heal the passivity layer. So this is okay on a very small scale where you might have an anodic reaction occurring, but the cathodic reaction kind of makes up for it and maintains the passivity layer. But the key here is that the steel is, in a perfect world, that will happen if the steel is homogeneous in composition. But again, it's a man-made alloy. There are imperfections in the steel, in the surface, and the chemistry of it, and that causes problems as well. Ultimately, what ultimately happens is that the iron atoms that are released at the anode sites are combining with OH groups to form iron hydroxide minerals, and those iron hydroxide minerals then bind with more oxygen and water in the concrete to give more complex iron hydroxide minerals, and those iron hydroxide minerals combine with more water to produce, water oxide hydroxide minerals, right? And it just goes from there. And as each one of those iron hydroxide minerals are produced, that's the rust that we see. Okay, that's the orange brown rust that we see, and pretty soon the formation of rust chokes out the ability of the passivity layer to rejuvenate itself, and the pits and corrosion, the pits and corrosion that are affecting the steel just become more and more pronounced, and the steel is dissolving away, but reprecipitating as this rust, quote unquote, elsewhere. And visually, this is what we see, right? We see the surface of the steel is pitted where there's no protective paint, right? It's just exposed to the oxygen and water, and it's just starting to disintegrate away. A little easier to see it maybe in this way. The top diagram shows an embedded steel, say rebar, for example, coming in cross section. The top surface is most affected by the influx of chloride and oxygen and water, right, coming from the surface. That's and that's where most of the iron hydroxide minerals are forming or piling up at the top, where everything is combining, and the formation of those iron hydroxide minerals is again causing the concrete to crack because of a volume expansion of when that stuff forms. Just to give you an idea, from going from native iron all the way up to the different iron hydroxide mineral variants, you could experience maybe a 6.5, a factor of about 6.5 of volume expansion from the original embedded steel to how much volume is being taken up after all these iron hydroxide minerals are forming. So about could be up to 6.5%, 6.5 times what it started off with. And in the real world, this is what you see, right? These are pictures of a sidewalk surface where you can see that iron hydroxide material coming up to the surface, right? You can see pop outs because of what's oxidizing and corroding underneath there, causing the concrete to pop out. And on here's another example. This is around a window. We're looking at a window opening, and this is embedded steel in there, clearly popping out the concrete. It was also discussed pretty heavily that the corrosion of the embedded steel within the Champlain Towers condominium in Florida may have been responsible for the whole thing to collapse back in 2021. So just a quick wrap up here about how to prevent embedded steel how to protect it from corroding. If you can use chloride-free aggregates, cement additives, water in the concrete mix, that will help. if you can eliminate or limit the exposure of your hardened concrete to de-icer, de-icing salts or any chloride-bearing chemicals, that would be good. If you could limit your exposure, limit the exposure of the hardened concrete to seawater or seawater spray, that would be good. And also ensure adequate cover over the embedded steel. And Steve can touch on this a little bit more, but the amount of concrete that's covering your steel from the outer surface of the concrete down to the depth of the embedded steel, that's important. The deeper it is, the harder and longer it's going to take. The longer and harder it's going to take that stuff, the embedded steel, to be exposed to the water, oxygen, and chloride. And then lastly, if you can use low permeability concrete, that's optimal. And we all know that, again, concrete is both porous and permeable, and the permeability and porosity, it's a function of how much air is in the concrete. Is it entrained air, entrapped air, so on and so forth, the water cement ratio. So a lot of factors are going into that. With that, I'm going to hand this over to Steve, and he'll carry us on to the second half. Thanks, Steve.
Okay, sorry about that. All right, so I'm going to talk about identifying corrosion in the field, different ways to identify it. Chris showed a bunch of different pictures. Sometimes it's pretty obvious, visual evaluation. That's sometimes a pretty easy way to identify it. I've got ACI 228.4 listed up here. That's a really good document. I like it. It supersedes 201.1 if anyone's familiar with that. It's a guide for conducting visual condition survey in the field. It's got a lot of really nice photographs. It's got a lot of definitions, good terminology. I think as engineers, it's important for us to all kind of speak the same language. So when we're talking about spalls or pop outs or different types of cracks and fractures and things like that, this 228.4 document really helps to visualize, again, kind of defines a lot of those terms that we use. Another good document from FHWA is the Alkali Aggregate Reactivity book. We're not talking about alkali aggregate reactivity today, but a lot of times, again, this book's got a lot of good pictures in it. But a lot of times you might have cracks that develop from ASR that might be a pathway, for chloride ingress and things like that. So it's just a good book to be familiar with. Again, it's got a lot of definitions and photos. Manual sounding, kind of old school, but pretty effective. ASTM D4580 talks about a chain drag. You can use a rotary percussion tool. 4580 also talks about some electromechanical methods like impact echo, which is specifically covered in ASTM C1383. It's kind of a little bit more of a high-tech sounding tool. Half cell corrosion potential, ASTM C876, which I'll talk about shortly, kind of helps us to figure out the probability of active corrosion at the time the test is being done. And then obviously we can sample the concrete for various chlorides, water soluble, acid soluble chlorides, which I'll talk about those shortly also. So just a couple of visual photos. Identifying, you can tell by stains. Chris talked about rust. Sometimes precipitates might come out of the concrete from cracks. There might be some efflorescence. There might be spalling. The picture up there in the top right, that's a picture of a spall. I don't think it's any mystery on why it spalled. You can see the reinforcing steel kind of corroding and rusting away underneath there. Some rust stains down there in the lower left-hand corner. Can see a little bit of exposed reinforcing steel and the bottom of some of these ribs. But again, just visually, sometimes you can tell what's going on. There's another picture. some spalled concrete from a wall. Um, this this reinforcing steel has very, very little concrete cover. And I took this while I was walking around. It was a local college campus here in the Albany area. And we know college campuses, they put a lot of de-icing salts on their walkways, and this is obviously right next to a walkway. So maybe those de-icing salts are, getting thrown up against the wall and just kind of permeating into the concrete. And those chlorides are causing, kind of accelerating the corrosion. Another similar picture here, we can see a big spall on the underside of an elevated slab. So what happens here when you've got a lot of reinforcing steel, it's all kind of corroding. It's all at the same elevation. Chris had mentioned that as the steel corrodes, it expands in volume. So it creates all of these tensile kind of radial cracks from tensile stresses as this reinforcing steel expands from the corrosion. And what happens when you got all of these in a line together and they're all kind of on the same plane, you get all these radial cracks. Eventually they all kind of connect, and you get a big chunk that initially was delaminated, and then it falls off and becomes a spall. Similar situation here, although no spalling is going on, but there's definitely some delaminations. You can see some efflorescence up here. This is looking at the underside of an elevated slab. On the other side of this slab is a roadway surface that gets salted quite a bit. We actually went up here, we took some samples of this material, looked at it under scanning electron microscopy, and were able to figure out what the elemental composition was. It's essentially sodium and chlorides. So it was salt. Definitely some water infiltration coming through here. You can actually see some water stains on the side of this beam right here. So we know there's some leakage going on here. No mystery here. We've got some exposed reinforcing steel. We got some exposed stressing strands here. We got this top flange is kind of cracked and delaminated. Definitely an unsafe condition. This beam was actually shored up not long after our site visit here. So I mentioned half cell corrosion potential, ASTM C876. Like Chris had mentioned, corrosion can fundamentally be described as an electrochemical reaction. You've got electrons moving around, and if you recall, those electrons are negatively charged. So what we're doing with half cell testing is we're measuring the electrical potential within the concrete itself. We usually set it up on a grid system, and we take individual tests. You can see down here in the bottom right-hand corner, we've got one electrode that we pretty much put right on the surface of the concrete. This other electrode is attached to the concrete reinforcing steel. One of the things we always make sure whenever we're doing this half cell testing, we want to make sure that the reinforcing steel is all kind of connected. It's electrically continuous. So we'll expose reinforcing steel, maybe in the top right corner or northwest corner, and then in the southeast corner. And then we put a no meter on it, like what you see here in the picture, and we just make sure that there's electrical conductivity. But again, we kind of set up a grid system, maybe every 1 foot in each direction, maybe every 2 feet, depending on the size of the slab. And we measure the electrical potential with this ohm meter. And the more negative the voltage is, we're typically reading things in millivolts. So this is like negative 100 millivolts. The more negative that reading is, it kind of implies that there's more a higher probability of active corrosion, because that's what we're measuring, is those electrons moving around. And remember, those electrons are negatively charged particles. So the more negative the half cell reading is, it kind of implies that there's more electrons moving around, so that there's a higher probability of active corrosion. And again, that's what this half cell test does, is it gives you an idea of the probability of active corrosion at the time of the test. So what we do, we plot all of the values. We kind of make this equipotential map, kind of like a topographic map, but with the electrical potential readings. And any readings that are less negative, I know that's a double negative, but less negative than minus 200 millivolts. That means that there's not a lot of electrons moving around. It's not very negatively charged. 90% or a higher probability of no active corrosion at the time. Minus 200 to minus 350 millivolts is kind of, in conclusion, it's in that, range of, something might be going on, but we're not sure. If it's more negative than 350 millivolts, the test method says that there's a 90% or higher probability of corrosion at the time. So what we've got here is a drawing of a parking garage, or a section of a parking garage that we tested. These panels are about 30 feet long in this direction, and they're about 8 feet wide in this direction. And there's a joint in between each panel, and this is where the joint is. And you can see where the joints are. That's where we're getting most of our, the highest potential for corrosion, because we know what happens in the joints, right? If the joints aren't sealed up right, there's water getting in. It's a parking garage. People are coming in with salt on their cars, and they're parking. It's all that salty, slushy snow is collecting on the deck and kind of seeping in through these joints. And it was pretty obvious what was going on. This is another project, a little bit smaller, but kind of a similar situation. This is an overhead door right here. This is outside to the elements here on the left. So this is a garage on the inside. People would pull their vehicle in here. I think it was kind of a maintenance bay. And same thing would happen. It was an elevated slab. The snow and the slushy, salt-laden snow would basically melt and collect. And this area right here was an area of high probability of active corrosion. And we could see it from underneath. Also, there was some visual signs underneath. There was some delamination, no spalls on the top surface, but there was some delamination on the top surface. So we're talking about chlorides, chloride ions. There's different ways that you can test for chlorides. Probably the most common way is from a core. We'll go out, take a core, somebody will give us a core, and we'll test that core for chlorides. We usually like to test at various intervals throughout the depth of the core to kind of give us a chloride concentration profile. It's typically going to be higher at the surface and lower as you go in. So if we know our reinforcing steel is at like 3 inches or something like that, we might target that 3-inch depth and see what the chlorides are. Two different types of chloride tests for the most part. One is acid soluble, the other is water soluble. The acid soluble test will give you the chlorides, the total chlorides in the system. That's everything in the aggregates, admixtures, everything. And water soluble chlorides only gives you those chlorides that dissolve in water. And ACI 318 references the water soluble test method. It's those water soluble chlorides that are most commonly going to be is going to kind of contribute to the corrosion. I do want to mention, you want to be aware of the units when chloride values are reported. You might need to convert them. Most of the time, chloride values, testing labs will report chloride values by mass of concrete. ACI 318 lists it by mass of cement. I'll talk about that a little bit more in a minute. I mentioned sampling through cores. We can also sample in place. This is pretty much how we do it. We got a hammer drill. We drill into the side or drill into the top. We basically collect the dust at various intervals. It looks like this might be maybe from 2 inches to 3 inches. Notice this this person's wearing gloves, so we're not contaminating anything through sweat or anything any contaminants that might be on our hands. So this is an excerpt of the table from ACI 318 19.321, and it gives us the maximum water soluble chloride ion content permissible by 318, depending on what your exposure conditions are. So if you've got low exposure conditions to chlorides, exterior chlorides, you can have a higher concentration. If you've got high exposure to chlorides, then obviously you want to start out with a lower concentration. This is for non-pre-stressed. This is all pre-stressed over here. So pre-stressed concrete, you don't want to have any. You want to have very low chlorides in pre-stressed concrete. I mentioned the units and being aware of units. So again, they're typically reported. We take a sample of bulk concrete, and that includes everything, right? The whole concrete matrix. So when we run the test, we report the value in percent by mass of concrete. But here in ACI, ACI 318, all of these values are percent by mass of cementitious materials. Well, if you don't know how much cement is in that concrete mix, you might need to make some assumptions and do a conversion. The conversion is pretty easy. If you're provided percent chlorides by mass of concrete, which is again typically the value that a testing lab will provide, you just multiply it by 100 divided by P, where P is your percent of cement in concrete. And again, if you don't know what your cement content is, you can make some reasonable assumptions, which I've kind of listed out here. Again, lab gives you percent chlorides by mass of concrete. The value is 0.01%. We can assume, some fairly good assumptions of unit weight of concrete of 145 pounds per cubic foot. That's non-reinforced. So we know there's 27 cubic feet in a yard. So that's our unit weight per yard. We can assume, say, 564 pounds of cement in a cubic yard. That's for some of us old timers, that's your traditional 6-bag mix. And then you can calculate P just by taking the that 564 divided by 3915, which is our unit weight of concrete, multiplied by 100 to give us a percentage of 14.4. So we plug that into our formula. 0.01% by mass of percent chlorides by mass of concrete is what we're provided. Multiply that by 100 divided by 14.4, we get 0.069. That is percent chlorides by mass of cement. Again, that's with these assumptions. For pre-stressed concrete, that wouldn't be good because the ACI table says 0.06 is a maximum. I will say that that those values that are provided in ACI 318, that's for new construction. So it's just something to be aware of. So we just want to kind of summarize a few things that we've talked about. Sound concrete offers inherent protection against corrosion. That's the passivity layer that Chris talked about. The high pH, 12, 13 on a pH scale. We know corrosion is basically an electrochemical reaction. You got different, electrons moving around. Different forms of iron oxide being created as the steel corrodes and oxidizes. Corroded steel has a significantly larger volume than non-corroded steel. which is one of the reasons why you get, you know, the spalls and delaminations and things like that. You know, those tensile stresses building up in the concrete when that steel is expanding. You can see it a lot of times if you know what to look for. It can be pretty obvious sometimes. There's some high-tech methods, some low-tech methods to kind of help identify corrosion in the field. A lot of them are kind of related to sounding, either electromechanical sounding or just physical sounding with a hammer or, you know, a chain or something like that. And then different methods of sampling or testing for chlorides. You know, if you want to get an idea of, you know, what that concentration level is deeper inside your concrete, you know, again, maybe at that 3-inch, you know, 2 or 3 inch depth, which is right about where your reinforcing steel usually is. So those are some of the key points we talked about